Okay, what I'd like to do now is I'd like to explore p-threads, which is a technique of doing threading that's available in C++. We're actually also going to look at how Java does threading a little bit because it does some really interesting stuff. Okay, so this is a diagram that's reminiscent of the dispatcher worker thread pattern that we looked at in the last lecture. So it just shows another version. The version we looked at last lecture was the prime number server. So we had a client, actually multiple clients that could attach to the server and look for um, look for send in a number and the server will return whether that number was prime or not. So this is a different example, but it shows the same sort of dispatcher worker pattern. So what we have here is we have a browser, but we could have multiple browsers, and they're attaching to a web server somewhere out on the internet. And each time a browser connects to the web server and asks for a web page, the web server itself uses the dispatcher worker thread pattern to respond to the browser's request. And the idea is, behind this is that if we have multiple web browsers making multiple simultaneous requests, it's still possible for a single web server process to be able to respond to those requests and scale to them. And of course, you need to have enough hardware to support that, but this is a very common pattern. So what does this dispatcher worker thread pattern look like? Well, the web server process is running a dispatcher thread here. So that's my little picture of the dispatcher thread. But the loop that it's running is basically here. While true, get the next request and hand off work to for that request. And then we go back and get the next request again. So the dispatcher thread is just simply running this continuous while loop, waiting for more and more browsers to connect. Every time a browser connects, we hand off the work. Now, if this was not a threaded approach and all of the requests that we got were handled synchronously, the way things would work is when we get the next request from, let's say browser A makes a request. When we get the next request, we then hand off the work for browser A. And then when we are done handing off the work for browser A, we can go back to the top of the while loop and get the next request. So if we had that kind of architecture, what would happen is that we would only be able to handle one browser request at a time. And there goes the awesome website that we wanted to build that could handle lots of folks attaching, connecting to it all at the same time, making requests. It wouldn't scale very well. So instead what we do is after we get the request, which is handled in the thread space of the dispatcher thread, we then create a new thread called the handoff work thread. And that thread executes independently of the dispatcher thread and any other worker threads that are around. All right, the work that handoff work does is over here, basically gets the work it needs from the browser, does some cache lookup to figure out if the page that was requested from the browser is in the cache or not. If it's not, it goes to disk and stores, the process of doing this lookup disk will store that page in the cache, and then it returns the page to the client that's making the request to the web server, and then it finishes. But all of this work here is handled independently of this work, and all of this work here is also handled independently of any other browsers that are connecting and executing their own handoff work threads. So that's what you see here. This dispatcher this dispatcher thread has several worker threads that are doing this handoff work independently. And so each one of these worker threads is connected to a different browser. So maybe this worker thread is connected to this browser, this one's connected to another one, and this one's connected to another one. So that's another sort of review of the dispatcher worker thread and a design pattern. And it's kind of making the case for, hey, threads are kind of a good idea. They're a very useful idea. All right. The thing that's important to realize here is this lookup cache, right? That's memory that's shared across multiple threads. And it's very easy to share memory in a single process. It's a little bit more work, actually a lot more work, to share memory across multiple processes. So um, starting up a thread that's sharing memory between an existing threads is a really useful technique. And that's why threads are really attractive as compared to the heavyweight concurrency that we get from something like a fork. We're also going to look at some other reasons why threads are superior to the heavyweight concurrency of fork in just a little bit. Okay, but I really want to drive home now sort of the details of the difference between what happens when you do a fork and you create a separate concurrent executing process and what happens when you do a thread where you create concurrency within the current process. And to do that, I want to draw some pictures for you. So I'm going to just move this up here, and I'm going to draw a diagram. Make this a little bit smaller. A diagram of the execution space, the process space of a process. All right, so there's a few pieces to a process space, right? So one chunk of memory associated with the process space is the code, all right? Clearly the instructions that have to be executed to run your program have to be stored somewhere in the process space of the computer program. All right. We also have static data. So static data would be things like a global variable, or if you had like a Java class, it'd be something like a static member. We also have the heap. So this is where data that you carve out using something like new would go. And we also have file handles. We know about these because those are things that can be shared across processes. For example, pipes create a form of a file handle that can be shared across processes. If you open a file before you do a fork, you have access to that information shared across processes. So that's some special data. And then I'm going to separate out another kind of data as well. So that is the register data. So this is like the instruction pointer and temporary data that's stored in registers as a result of a calculation or the result of a comparison operator that just happened. So that's register data. And there's also the stack. All right, so the stack comes about, there's housekeeping every time a method gets called, and there's also local variables that get created on the stack when you enter a method. All right, now what I want to do then is just draw a little diagram here of a single thread of execution. So if you write, pretty much all the any of the kind of code that we've been working on prior to operating systems, most likely you've had just a single thread of execution. So we could call this, if you want, we could call this the main thread. And as so you're already doing threading. It's just you just have a single thread. All right. So now, if we were to create a new thread, if we create a second thread of execution in your program, what does that look like? So I'm going to do a little bit of copying and pasting and editing here. Oops. Let's try that again. Okay, so if we have a second thread of execution, what's that going to look like? Well, a second thread of execution means that we have another thread that's running here. So I need a little bit of real estate to make this work. All right, so we're going to have a thread here, and we're going to copy that. Let's mark that again. And we'll put another thread here. So now we have two threads of execution in the same program. The thing that's interesting is that these threads get to share information in the program. They get to share data, and they share some of the data, but not all of it. So the way we divvy this up is that the code, static data, heap data, and the file handles, those get shared across threads. But the register and the stack data, those are not shared across threads. Those are, generally speaking, those are private and independent for each thread. Okay, so each thread gets its own registers and its own stack. Okay, that has a lot of implications for programming. And we're going to look at some examples of that in just a second. So let's take a look at some code to try to understand the difference between what happens when you do a fork to create concurrency and you create a thread to create concurrency. All right, so here's a piece of code. All right, so I'm going to use a slightly smaller pen here. So I have int, the int equals 42. And then I'm going to have an int main void. And I'm going to create a fork, do a fork here. And I'm going to check to see if I'm the parent or the child. So if the PID is greater than 0, I'm the parent. And I'm going to set the int equal to 99. And then I'm going to have an else. I must be the child. I'm going to set the int equal to 0. Okay, so what happens when we do a fork? Well, let's grab this diagram here and we can see what happens. Okay, so initially, I'm actually going to shrink this down a little bit too. Okay, so initially, when we start the program running, we have a single thread of execution here, all right? And the program has all these different areas of memory. Now, the integer, this integer is stored in static, and I should have said int the PID there, but this PID is something that's stored in the stack because that's a local variable, all right? Now, when you do a fork, what happens is a new process gets created that has a complete copy of everything that the original process had. So we're going to create a new process here. And what's interesting is that both of these processes have a single thread in them. So we'll call this the parent process, and this is the child process. Now, when the parent executes and sets the int equal to 99, what's going to happen is that the int was 42, but that's going to get changed to 99. And then the parent will basically exit. Child also has a copy of the static memory from its parent with the int equal to 42. Now, when the parent changes the int from 42 to 99 here, the child does not see that change because the parent is changing static memory in the parent's process space, not the child's process space. When the child changes the int to 0, then the child resets the int of 42 to the value of 0, and then the child exits. So both the parent and the child each have a single thread of execution, but they have their own copies of memory. So any changes the parent makes, the child doesn't see. Any changes the child makes, the parent doesn't see. All right? Now this is kind of a review of how fork works, but let's take a look at how threading works, all right? So I'm going to write the same code, but I'll write the code creating threading, all right? And this is pseudocode. We're going to write the actual code for the pthread syntax in C++ in just a moment, but I'm going to create something that's sort of approximate right now. Okay, whoops. The int is equal to 42. That's our global variable. And then int main void. So this is trying to mirror the code we just had, but do it in a way that lets us create a thread. Okay, so what we're going to do is we're going to say thread create, and we're going to pass the address in of the method that we want to use to create the thread. So we're going to create a method called start in a second. And then we're going to say the int equals 99. And that's the end of our main program. So the code in the main program is basically the code that the main thread, the initial thread, executes, all right? So the initial thread is going to create a new thread. That's what this is. And then set the int equal to 99. Okay, let's write the code for start. So the code for start simply sets the int equal to 0. All right, so that's the code for that uses threads. So let's take a look at what happens. Again, grabbing memory here. I want to think about how I want to, yeah, okay. We should do it this way. So let's grab our memory. Oops. Let's grab our memory here. So initially, when this program gets started, we have something that looks like this. A single main thread that's running, and we have a global variable, the int, that is stored in the static memory of the process. Now, when we do this thread create, what we end up doing, so when we do the thread create right here, what we end up doing is changing the structure of the memory in the process. And we do it like so. First of all, we don't have a single thread anymore. We have two threads. So we'll put one thread over here, and we'll put a second thread. Whoops, that's not good. We'll put a second thread over here. Okay, so now we have two threads. All right, and there's a little bit of reconfiguration of the register and the stack. So we're going to change that and set this up so that the register and the stack are, there's separate register and stack for the main thread and the thread that just got created. Okay. Now, this was the original thread. And this is the new thread that just got created from start. All right. So I guess I don't have to, I'll call this main thread since it's from main. All right. Now, the thing I want you to notice is I did not make a copy of the process space to create the start thread. So I'm going to repeat that. I did not make a copy of the process space to create the start thread. Instead, what I did is I said, okay, there's a new thread in town called the start thread, and it gets its own register, set of registers for any work that it's doing, and it gets its own stack space. So as start calls additional methods, those methods will use up memory on start's local stack. Main continues to use its original stack space, and it also has its own private copy of registers. So like if start does a Boolean expression and something's greater than something else, that doesn't set any flags in the registers that impacts main. Right? So start and main can execute independent of each other. But the interesting thing is, what happens when the int, which is 42, gets set equal to 99? So here in the static area, we have the int equal to 42. All right. So once the main program does that thread create, it then executes this line, the int equals 99. So the 42 goes from 42 to 99. But in the start code as well, the int gets set to 0. So then maybe the int goes from 99 to 0. But here's the thing. Both the main thread and the start thread are executing at exactly the same time. So we really can't say which one of these is the last instruction to execute. We can't say that the int equals 99 goes first and then the int equals 0 goes second, because we have no control over the order that the operating system chooses for which instruction gets executed after this thread create. So maybe the order that things go are the int starts at 42, then becomes 99, then becomes 0, or maybe the int starts at 42, then becomes 0, then becomes 99. Either of these is possible. And which one is going to happen is not possible to determine. It's non-deterministic. That should freak you out, because basically what I'm telling you is that this program here, which is just a few lines of code, you cannot predict what this program is going to do. Every time you run it, it's a little bit like rolling or generating a random number, and some of the time one thing happens and some of the time the other, but there's no way to predict it. That should freak you out. You have code now that's running that you cannot say what it is going to do each time you run it. And there's no random number generator here. It's just the fact that you decided to use some concurrency. So when you're not careful about how you do concurrency, you can get this non-deterministic behavior, and it's something you have to be aware of. Okay, so what I'd like to do next is I'd like to jump into some code, and maybe what we can do is write a little bit of code that actually does pthread create and demonstrates how to do some concurrency using threads.